I think I also said yesterday incorrectly that office hours for this class are Tuesday and Thursday. I meant Tuesday and Wednesday. Okay. And again, if you need help, probably the best time to get help, if it's just a quick question, especially, is just right after class, especially if you let me know ahead of time. Not an issue there. But for the most part, I mean, you see how packed these times are. I mean, we're trying to cover a lot of material in class. So if you need help, if you want to go over some homework, I'm happy to. I really enjoy that. But come to office hours or let me know, hey, I'd like to stay after class today or something like that, okay? All right. So this section is an interesting one. They actually didn't do too much of this, when they taught this course out of different books. The last couple of books that they've chosen, they've tried to emphasize this a little bit more. But this is the precise definition of a limit. And anybody that's interested in going on into higher mathematics, getting a degree in math or something like that, this should be of particular interest and something that you should spend some time getting used to. A lot of times this is a bit of a struggle, figuring out, my gosh, how does this work? And why would they have all of these weird symbols in it and stuff like that? But we just kind of want to get a sense for what's going on here. So the reason we want to do this is up until now, we've been talking very informally about limits. Again, we've been using the words approaching, getting close to. We've been looking at graphs and stuff like that, using numeric evidence, using these algebraic and analytic techniques that we talked about yesterday in order to find limits. Well, now we want to talk a little bit more precisely about what exactly a limit is and what it means when we say get really close to. Okay, we want to be really precise about that. Okay, so if we take a look at example 1, I've got a nice picture here. It's all drawn for you. So a lot of this is just going to be kind of thinking. We're going to do a little bit of filling in the blank. I have notes that are all filled in. So really, if you'd rather just sit and watch the entire time and think about what we say, you could sit back and just watch. I'm happy to email you the notes. If you want to rewatch this video, it'll only take 50 minutes and then fill it in then. It's really important that you think about why somebody would want to do this and how this works the way that it does, okay? Because, I mean, especially on an example like this, it's like, well, no, duh, that's the answer, okay? So we've got this function right here, 3x, and I'm interested in finding the limit as x approaches 4 on 3x. And it's easy to tell by substitution. There's nothing weird that happens on that. The limit is 12, okay? You can look at the graph. It actually has a point there. We can do it by direct substitution and stuff like that. So what we mean is f of x gets closer and closer to 12 as x gets closer and closer to 4. Again, implied that from both directions it approaches that. So we want to be really precise about this. And this is where we get into, well, what do you mean by get close to? What does that mean, get sufficiently close to or get really close to? Well, here's what we're talking about. So we're going to start with the question. How close does x need to be to 4 so that f of x is within, and we're going to make up this number. I contrived this so it would work out nicely. Okay? How close does x need to be to 4 so f of x is within about 3 units of 12? If the point of interest is 4 and the limit is 12, how close do we need to be to 4 so that we're within about 3 units of 12? Okay, that's what we're going to start with. And the numbers for this are going to work out really nicely. Okay, so again, this is the point of interest. Okay, this is what we think is the limit, what we can tell by just looking at the picture. And what we're saying here is we're giving ourselves a little bit of error. We can be within 3 units or 2 units or 1 unit or maybe half a unit of 12. We're giving ourselves a little bit of leeway, and we're going to call that leeway the error, okay? And we're going to use the Greek letter epsilon to represent the error, okay? It's kind of a funky looking backwards 3 or a funny looking E for epsilon, for error, if you want to think of it that way, okay? So that's how much error we're allowing ourselves. Everybody good with that? Okay, so now we're going to translate this into a mathematical expression. So if we say f of x is within 3 units of 12, it will correspond to this inequality right here. And let's think about why that's the right inequality, okay? So within 3 units of 12, f of x within 3 units of 12. So here's the function 3x, and then I'm subtracting 12, and then I put that in absolute value, and I say that's got to be less than 3. Well, the difference between the function and what the limit is, we do a subtraction problem for difference. And the reason we put absolute value is We didn't say we care about whether or not we're below the limit of 12 or above the limit of 12. So by putting absolute value on there, it allows us to be above 12 or below 12, and we can still calculate a difference. And then we make sure that that difference is less than 3. Does that make sense? Absolute value doesn't care which direction, it just cares how far. And we want to make sure that the distance that it is from 12 is less than 3. Okay? See why we need absolute value on there. It may not be fun, but that's why we need it on there. Okay? So again, this right here is the function. So we're going to generalize this in a couple minutes. We're going to generalize this. This is the function. This is what we think is the limit, and this is the allowable error. So this is the function, this is L, and this is epsilon. All right? Now, if we were to solve that inequality, it looks something like this. You'll remember that there are two cases when you solve absolute value inequalities. Okay? One for each of the directions. So if we just take the absolute value off, we're solving when 3x minus 12 is less than 3. Okay? If we introduce a negative, we'd have to switch the direction of the inequality also. Okay? So it basically says this difference, whether it's positive or negative, has to be between -3 and +3. Well, we're allowing ourselves to go up 3 and down 3 from right there, from the 12. Make sense? Okay. So it's kind of like a three-sided inequality that we can solve here. Okay? So what we're going to do to solve this is we want to get x all by itself. So I'm going to add 12 here, and add 12 here, and add 12 here. So I'm going to write this line a little bit weird. We're going to do the math in just a second. So this is going to be 12 minus 3 less than, this would just be 3x less than 12 plus 3. And then again, just as a little hint, algebraically, this represents the idea that I can go up 3 from 12. I can go up here and still be within my little allowable error. Or I can go down 3 from 12, go down to here, and still be within my allowable error. Does everybody see what that line represents? Okay. Well, I mean, realistically, we're going to write a 9, we're going to write a 3x, and we're going to write a 15, right? And then we're going to finish solving by dividing by 3. And I end up with this. I end up with 3 less than x less than 5. So remember how this question started out. If you want to be within 3 units of 12, how close do you have to be to x? Well, you've got to be between 3 and 5. Well, 4 is smack dab in the middle of that little interval there. So if we said, how close do you have to be to 4? How close does x need to be to 4? So f of x is within 3 units of 12. Well, you're allowed to go either direction, but how far can you go in either direction? 1 unit. Okay, this is a symmetric interval around 4, so you can go 1 unit in either direction. So it's a symmetric interval around the point of interest. I can go 1 unit in either direction. Now, if we take a look at the picture, does it make sense that if we allow ourselves to go up 3 and down 3, that we'd be allowed to go over 1 and back 1 from that point of interest and still be within our allowable error? Does that make sense? Okay, hopefully it does. Why? Can somebody tell me why that makes sense? Why it would be 1 unit on either direction? One?
Your equation is 3x. So if you plug in 1 less, you get 3 less. So if you plug in 1 more, you get 3 more.
Okay, on the right track. Did you get that?
So our equation is stretch 3 in the original function. So.
Stretch 3. I like that. Good thinking there. Over 1, up 3. Back 1, down 3. It has to do with the slope. It's exactly the same slope on either side. So yeah, if you let me go up 3, I'm going to go over 1. And if you let me go down 3, I'm going to go back 1. Okay? It has to do with slope. Does everybody see that? Okay? So hopefully the answer there is yes, that makes sense. And it has to do with same slope on both sides. Good there? Okay, so in order to make this process a little bit more uniform so that we can generalize it and do other problems, okay, we're going to assign some symbols, okay? if f of x is going to be within 3 units, now before we said 3 units was our allowable error, this is going to be epsilon. 12 was the limit, so that's going to be L. So if we're dealing with errors and limits, if we're dealing with y values, these are the two symbols that we're going to use. And then it says x must be within 1 unit of 4. Well, this again was the point of interest. Okay? Usually that's going to be an A. And this, we're going to use this symbol right here. I'll try and draw it kind of accurately. That's okay. What is it? Okay, it's the Greek letter delta. Oops, Greek letter delta. Okay, so we've got the Greek letter epsilon for the allowable error in the y direction, and we've got the Greek letter delta for the allowable difference in the x direction. Okay, so epsilon is going to go with the limit and the y values and the function values. Okay, delta is going to go with the x values. So epsilon error, delta difference. Everybody good there? Okay, so in that previous example, the interval was symmetric about 4. We went from 3 to 4.5. So we went 1 unit in either direction. And that made sense based on the graph. But what if we went through our work and for some reason it produced this interval? We could stay within the allowable error if we went down to 3, but only up to 4.5. So we've got 4 right here, and this is what's happening. I can go all the way down to 3 on this side, but on this side I can only go to 4.5. So now it's asymmetric about the point of interest. You might want to think about what would produce that. We're going to talk about that in just a second. Okay? But now how close does x have to be to 4 so that it's within 3 units of 12? If we want to guarantee that the function values we get are within 3 units, I can go 1 unit down or I can go half a unit up. But I want to make a statement. I want to say how far I can go in either direction. It doesn't matter which direction you go. I can guarantee you you're still going to be within 3 units of the function value. Half a unit, okay? So this is what we're going to do. We're going to say this is delta 1. And we're going to say this difference over here is delta 2. Well, I'm allowed to go 0.5 units on this side, and I'm allowed to go 1 unit on this side. So if those are my two choices for delta, which one would I choose to guarantee that regardless of which direction I go, I'm still safe? I'm within that allowable error. Delta 2. I take the smaller of the two. Everybody see that? Okay. So I'm going to be 0.5 units within 4. Because if I went down to 3.5, am I still safe? I am, okay? If I chose delta 1, then I could choose 4.75, and would I still be safe there? I wouldn't, okay? So if it's asymmetric about the point of interest, you always choose the smaller of the two deltas, okay? Lock that away. So it says, under what circumstances would the interval not be symmetric about the point of interest? Well, let's take a look. On that previous example, we looked at why was it symmetric? Because we had the same slope. So how could we make one that's asymmetric? Have different slopes or different steepness on either side of the point of interest. So let's take a look at this one right here. Again, a very familiar graph. X squared. Point of interest is 1. And we're going to allow epsilon to be 1. All right? So the limit is 1, of course, and we're going to allow an error. So let me blow this up just a little bit. We're going to allow epsilon, an error, we're going to allow that to be 1. So I can go up to 1 and I can go down to 0. So if this is the limit, and that's the point of interest, we'll call that an A. Okay, if I follow this one over here and down, what is this point right here? If this is x squared, what is it? Radical 2. Okay. What do I plug in to get to 2 on the, what do I plug in to get a 2 out of this? I plug in radical 2. So this is radical 2. Okay. And this one's kind of interesting. If I go down here, what's the x value that produces 0? 0. Okay. So my interval looks like this. It goes from 0 to radical 2, and 1 is about right there. So if I looked at the interval like this, and I said, all right, let's figure out what delta 1 is, and let's figure out what delta 2 is. Okay, what's delta 1? No, how far is it from our point of interest to the end? Okay, 1 unit. Okay, how far is it from here to here? A little less than 0.5. It's approximately 0.41. Okay, if we wrote it down correctly, if we took the bigger of the two numbers and subtracted the smaller, it's precisely radical 2 over 1. But let's say that it's 0.4. Okay, approximately 0.41. Okay, so if this is delta 2 and that's delta 1, what's delta for this problem? Which of the two do I choose? I choose delta 2, so I'm going to choose 0.41 approximately, and then precisely that's what it would be. Okay, so what this means is if I go over here 0.41, I'm still within 1 unit of the limit. And if I go over here 0.4, yeah, I'm guaranteed because I'm about right there. Okay, so that's an example of one that's asymmetric. And again, why is this? Take a look at how steep the graph is here compared to how steep the graph is here. It's steeper here, so we cover that 1 unit in error a little bit faster. It doesn't take much difference in the x-coordinate to produce that 1 unit of error. Okay, this is much more shallow, so we have to go all the way over here before we get that 1 unit of error in the y direction. Does that make sense? Okay, let's take a look at this example. Function is 1 over x. Point of interest is a equals 2. So here's a equals 2. And we're allowing the error to be 1/2. So if I were to follow this over, what is the limit as x approaches 2? It's 1/2. Okay? So there's the limit, 1/2. Okay? And what is my allowable error on this one? 1/2. So that means I can go up to here and down to here. There is my L plus epsilon, and there's my L minus epsilon. I'm here and I'm here. I can go up 1/2 unit and down 1/2 unit. So I'm looking at 1 and I'm looking at 0. Any questions? Yeah. So we'll get there. You're on the right track, but we're going to get to something that I think addresses your concern. Okay? So if I follow this one over, if I go over to 1 on this curve and I follow that down, where is this on the x-axis? It's at 1. Okay? Well, again, if this is 2 and that's 1, I can figure out what delta 1 is. How far can I go on that side, in that direction, and still be within 1/2 unit? I can go 1 unit. Okay? Now, 1's going to be all over this. If I follow this over here, when does that hit the curve? It never does. So technically speaking, how big is delta 2? Yeah, you can go as far as you want. Now this should be an easy choice. Of delta 1 or delta 2, which one are we going to say, all right, you can go this far and I can guarantee you're within 1/2 unit of the limit. It's going to be delta 1, so it's going to be 1 unit. So there's delta. Again, the reason we have different deltas on either side, the reason it's asymmetric about the point of interest is because we have different steepnesses, different slopes. This gets really steep. This is really, really shallow. I mean, it really flattens out there. We've got that horizontal asymptote. Any questions?
So were we just finding delta in that?
Yep, that's all. And you've got some problems where that's all you're doing, and they're not even this difficult. They got nice pictures for you and everything. Okay? All right. So when would the interval not be symmetric about A? When would it not be symmetric about the point of interest? When we have different steepnesses or slopes on either side. Okay, that's one. Okay, now you can sit back and relax just a little bit because on the bottom part of this page there's really not much to write down. I copied the textbook definition, the one that they use in this particular textbook anyway, and then we're going to translate this into words, the concept or the idea, and what we do in practice, okay? Because this is going to sound a little bit weird, like why on earth would anybody do this? But there are actually people who do this all day. They do research like this. Okay, and they use symbols like this. So here's the textbook definition. It says, let f be a function defined on some open interval. So it's got to be defined on this little interval. And it contains the number a. A is important because it's got to contain the point of interest. Okay, so we know it's defined on this open interval. Okay, it contains the point of interest, and it's defined everywhere except possibly at a itself, because we don't really care what happens right there. We just care what happens around there. Then we say the limit of f of x as x approaches of a is L, and we write this right here, which we've seen before. And then here's where we get into the nitty-gritty of this. If this is true, if for every number epsilon greater than 0, there is a number delta greater than 0, so that if that's bigger than 0, so in other words, if that's positive and less than delta, so in other words, if the difference between the x coordinate and a is less than delta, as long as you make sure that you're within this little delta window in the x direction, then the function values that you plug in on that little window will be within epsilon of the limit. Okay? So, yep, very confusing. Any positive number you pick for epsilon, so any allowable error in the y direction, will correspond to some allowable difference in the x direction. So you tell me how close you want to be to the limit, and I'll tell you how close you have to be to the point of interest. Tell me how close you want to be to the limit right here. Absolute value, because we don't care whether you're above it or below it. You give me an allowable error, and I'll tell you how close, what the difference can be in the x direction, how far you can be from the point of interest to fall within that allowable error. Okay? So this is like a sick mathematical game. That's what it is. Okay? So in words, if we were to say this, you can just read that sentence as well as I am. That is what it says in words. And if you study this for a long time, and I first saw this definition probably 22 years ago, okay? And it took quite a while to really get, okay, this is what they're talking about, and be able to apply it in a lot of different situations, okay? That's what it means in words. This is the idea. If you think you know what the limit is, you can state how close you want to be to that limit. Then you can find a delta, a number that says how close you need to be to the point of interest, so that your function value is within that allowable error, epsilon, of the limit. So if you're within delta of the point of interest, if you're within delta in the x direction, you're going to be within epsilon of the limit. Delta goes with x, epsilon goes with y. Okay? So here's where the game part comes in. This is basically what we're doing. We're going to guess, or we're going to be given the limit. Okay? Most of the time it's going to be pretty easy to figure out. We pick or are given the allowable error. So somebody says, look, I want you to prove to me that the limit is actually 12. You know, giving yourself 3 units in either direction, that's a pretty big window. How about 1 unit in either direction? Okay, I can find one to go along with that. How about half a unit in either direction? Okay, I can tell you what delta needs to be in that case. What if I allow you 100 in either direction? Can you find me one for that? Okay? And if you can do that, no matter what positive number they give you, so they could give you 1,000,000th or 1,000,000,000th in either direction. You can go up to 12 and 1,000,000,000th, and you can go to 12 minus 1,000,000,000th. That's the size of the window. How big would my delta window need to be in order to produce that? How far can I go in either direction from 4 in the previous example so that that's still true? Okay? See why it's a sick game? Okay, so we're going to pick or are given an epsilon, and then we find the delta. So they give us the allowable error, and we find the difference. Okay? Error in the y direction, difference in the x direction. Okay? In practice, this is actually pretty darn easy to do, especially because the problems that they've chosen for you to do, again, a lot of them have functions that are very easy, or they've got graphs, and sometimes it's literally as simple as picking out delta 1 and delta 2, and then picking which one? The smallest of the two, okay? So you have problems like this. All we need to do is, this looks confusing, okay? So let's just translate it into something that we understand. use the given graph of f to find the number delta such that if x is within delta units of 3, that's x, that's a, and that's delta. That's the point of interest. That's f of x. That's L, and this is epsilon. See how those things are in the same place as we looked at before?
Yeah.
So all we need to know is, well, the point of interest is 3, and we think the limit is 2. Okay, we've got this figured out mathematically. Let's make sure that this confirms what we see in the picture. Does it look like the point of interest is 3, and does it look like they're pointing out that the limit is 2? And they've given us a bunch of numeric values. Notice that we start at 2 and go up to 2.5. Start at 2 and go down to 2.5. This window, this epsilon window, will always be symmetric. It will always be symmetric because they're giving us epsilon. You have to be able to go epsilon in each direction. Got it? Follow this one over just like we did before, we get 3.8. Follow this one over, we get 2.6. All we have to do is identify each one of these. What's delta 1? 0.4. Delta 2? 0.8. Which one do we choose to guarantee that this statement right here will be true? Yep, so we say delta 1, or we just say delta at this point. Delta is going to be equal to, delta is going to be equal to 0.4. So if we were to write this out, if 0 is less than x minus 3 is less than 0.4. So as long as you're within 0.4 units of 3, then what? F of x minus 2 is always going to be within 0.5 units of 2. True statement. If I'm allowed to go down to 0.6 and up to 3.4, and I go up here and trace that over, and I go up here and trace that over, have we guaranteed ourselves that we're always within 0.5 units of the limit of 2? We have. See how that works? Piece of cake, right? Okay. Let's try and keep it that way. Okay. All right, so we're going to use the exact same example, but now we're going to try and apply that precise definition. So again, same function and everything. We think the limit's 12. This time we're going to change to an epsilon of 1. So this is what we want. We want the difference between the function and what we think is the limit to be less than the allowable error, less than the epsilon. So we start out with this guy right here. And what we want to end up with is we want to end up with a statement involving delta. Something that looks like that. So it's going to look like this down here. Here's how we're going to end up. So this is what we're going to do. Just like we did before, we're going to say negative 1 has to be less than 3x minus 12, has to be less than 1. The reason we get that is if it's a less than, it's going to be an and it's going to separate these two inequalities, these two separate inequalities, that one, and let me write it like this, 3x minus 12 less, or excuse me, greater than at that point, greater than negative 1. So both of these have to be true. If you think about it, you can do a kind of a pancake flip. Take this, flip it completely over. That would put negative 1 here, and then it would be a less than instead of a greater than. The 3x minus 12. It's a lot easier than solving them separately and then putting the answers together. Got it? And then solve. Notice how this one is the limit plus or minus 1. That's going to put us at 11. Notice how this one is the limit plus 1. That's going to put us at 13. Now the function is all by itself. The function can be as big as 13 and as small as 11. Look how that corresponds over here. And then all we have to do is figure out, well, how does that translate down here? What would my epsilons be? So let's divide by 3. This is going to be 11 thirds less than x less than 13 thirds, which would be a lot easier if we thought about it this way. This is going to be 3 2/3. This is x, and this is 4 1/3. And what is the point of interest? 4. So where does 4 fall in between 3 2/3 and 4 1/3? Smack dab in the middle. It's symmetric. How far do I go in either direction to get to these ends of my little delta window? Okay, the whole thing is 2/3, so in each direction I get to go 1/3. Does that make sense? Yeah. Okay. So the delta that I'm going to choose is going to be 1/3. So I've got the pattern right here. So if we were to state this to finish this off, look, you told me what epsilon was. Now I'm going to tell you what delta you need to make sure you're within epsilon. So we say as long as you choose a point whose difference from 4 is less than 1/3, notice how that's the point of interest and that's the delta we found, then your function minus what we know is the limit is going to be less than 1. So we found, let me make that a little bit more clear. We found the proper delta to guarantee us that we were within epsilon. Okay, any questions there? Okay. Now, I do want to show you one quick thing. So I'm going to erase this. It is possible on very simple functions like this to reduce just slightly the amount of work. I'm not a huge fan of this, but I do want to show you this because I think the textbook uses it. Notice what we want right here is we want the absolute value of x minus 4 to be less than some number. And we're starting with an absolute value right here. So what we do is we do something kind of clever. Is this okay to do algebraically? Yeah, we just factored it. Absolute value guarantees that whatever comes out is positive because it's talking about distance from 0. If the factor of 3 is already positive, do I need that inside the absolute value? No. Divide both sides by 3. That's okay, right? It's an inequality, but I'm dividing by a positive number. There it is right there. Okay? It is very slick if it's a linear function. If it's something that's not linear, I really wouldn't mess with that. Okay? If you want to take the time to figure that out and really study when it works, when it doesn't, and study how you can always take something and algebraically, without breaking it into two separate inequalities, figure that out, be my guest. Okay? If you're going into higher mathematics, that might be worth it. Okay? So here's what we're going to do now. Okay, to actually prove that the limit is 12, we don't want to go back and forth with somebody and say, okay, you gave me a 1, I gave you a delta. You gave me a half, I gave you a delta. You gave me a billionth, I gave you a delta. What we want to do is we want to say, look, give me any epsilon you want. I'm going to give you a formula that will tell you how you find delta. Okay, and that's what we're going to do next. So to actually prove that the limit is 12, this is what we do. We're going to use an arbitrary epsilon. So any positive number greater than 0. So it would work like this. We're going to start off with the same thing. We're going to start off with f of x is 3 and the limit is 12. And we're just going to use the symbol epsilon over here. So if I follow the same pattern, I had a negative epsilon here, I had a 3x minus 12 here, and then I had a positive epsilon here. I added 12 to everything, so this is 12 minus epsilon. That's 3x, and this is 12 plus epsilon. Again, notice how this is the limit minus epsilon, and that's the limit plus epsilon. There's our little epsilon window that the function's got to be within. And then I'm going to divide everything by 3. So this is what I end up with. I end up with 4 minus epsilon over 3 less than x less than 4 plus epsilon over 3. Now, that looks a little bit weird, but think about this. 4 is right here. This would represent 4 plus epsilon over 3, and this would represent 4 minus epsilon over 3. What do you notice? Yeah, you go the same amount on in either direction. What's delta in both cases? Epsilon thirds. I added epsilon over 3 and I subtracted epsilon over 3. So that makes delta equal to epsilon over 3. So, and I've written all this down so you don't need to write anything down there. If we were to actually state a conclusion for this, we'd say, given that function, you tell me any epsilon you want, then delta needs to be whatever epsilon is divided by 3. As long as you're within epsilon over 3 units of 4, the point of interest, then the function value is going to be within epsilon units of 12. That means the limit has to be 12. So, does that support the answers that we got in those previous examples? When epsilon is 3, what would you get for delta? You'd get 1. And isn't that what we got in our first example? If epsilon is 1, what would you get for delta? You'd get 1/3. So if we did say epsilon was, let's say it was 1,000,000th, what would delta be? Yep, it would be that number divided by 3, which would be 1/3 millionth. It would be 1/3 of whatever epsilon was. Does that make sense? Okay, do you see why this is better? This is kind of a pain in the butt having so many symbols floating around, but what we've done here is we've basically said, look, you can play your own game now. I've told you what the rules are. It's kind of like somebody saying, can you tell me how to solve any quadratic? Yeah. I mean, there are ways that are easier than the quadratic formula on some of them, but will the quadratic formula take care of all of them? Yes, it will. This takes care of all of the deltas for any epsilon you can give me on this particular problem. Okay? So you turn the work over to them. You say, hey, here's a rule. Okay? So if you flip over to the last page, we're going to take a look at another one. This one is a linear example, and that is a nonlinear example. And I'm hoping we have time to finish both of these. Okay? And then we've got a nice weekend coming up and all that good stuff, right? Okay, so we want to prove, not just show, but we want to prove that the limit as x approaches 4 of 2x plus 5 is equal to 13. So there's f of x. That's the limit. And that right there is a. What are we missing? Okay, well, we got to find delta, or at least a rule for delta. And we need epsilon. If you're proving, you're using this. An arbitrary epsilon greater than 0. So all 4 things that we need are right there. Okay? So again, we're trying to find the existence of some formula for delta. So here's what we've got. We're trying to show that if x minus 4 is less than epsilon, or sorry, delta, then f of x, which is 2x plus 5, minus, what do I put here? 13 is less than epsilon. Okay? Now let's just double check and make sure that we got everything right. Remember I was saying earlier, epsilon goes with the L and the function value. These are all y values. Okay? These are all x values. Epsilon window in the y direction, or the function value direction. Delta window in the x direction, in the point of interest direction. Any questions there? Okay, so this is what we want to show. Which one do we start with? This guy right here. Okay, so let's go through and do that. Here's what I've got. 2x plus 5 minus 13 less than epsilon. 2x minus 8 less than epsilon. You want to take the shortcut on this one since it's linear? Let's do 2x minus 4. Gosh, look how nice that is. Divide both sides by 2, and here's what I've got. Okay, now this book makes a big deal of putting this 0 here. The way we set this up, there's no way this could be 0. Because were we interested in ever actually plugging in a 4? No, because that's the point of interest. We don't care about the point of interest. We care around the point of interest. So there's never any danger of this turning into a zero. This book makes a big deal of this. Okay. So what we're going to say here is, if that's true, then 2x plus 5 minus 13 is less than epsilon. And then we can use these 3 dots. Anybody know what that means? It stands for the word therefore. Therefore, what have we proven? The limit as x approaches 4 on 2x plus 5 has to equal 13. So no matter what number you pick for epsilon, again, as long as it's a positive number, no matter how big, no matter how small, and again, we're interested in getting really close, so we're interested in plugging in really small epsilons. As long as you choose a delta that's epsilon over 2, take your epsilon, divide it by 2. As long as you're within that of the point of interest, we guarantee you that the function values are going to be within epsilon of the limit. That meets the definition. You want to be really close here? Get this close here, and I guarantee you. Make it smaller, we're going to make this smaller. Make this smaller, make this smaller. As long as you can continually do that, like this says you can, just take your epsilon divided by 2, you've proven that that's got to be the limit. Okay? We kind of squeeze it down there. No matter how small an epsilon you choose, we guarantee you can find a delta. Okay, any questions? Okay. I actually have the answer written down below here for this one. Okay. This is an interesting problem. Can somebody tell me why this would be interesting? I mean, the answer is 3. Clearly it's 3. Plug in a 2, 2 squared minus 1 is 3. You know the answer is 3, but we want to prove it using this epsilon delta definition. Okay, what makes this more interesting than the linear ones? Yeah.
We're working with the negative.
Working with this part? Okay, if we're looking at 2, we're actually looking right here. Okay, it does have some negative parts, which we haven't seen much of before. I've been trying to keep it relatively simple. Okay. What did we say was what?
Oh, it's not linear, so it doesn't have like same slope.
It does. It doesn't. Yeah, it has different steepness on either side. It's steeper over on this side than it is on this side. So we're going to get slightly different deltas. We're going to get a different delta 1 than we do a delta 2. And doing this, so I'll say this. There are tricks to do something like this. And if you want to find out what they are, that's great. We're gonna do it a way I think is a little bit more intuitive and will make a little bit more sense. But there are other approaches. Okay, so but none of them are easy. I'll put it that way. All right, I think this is the most straightforward. Okay. Ooh, let's see. Something disappeared here. We're going to use an arbitrary epsilon greater than 0 because we want to prove. I'll have to find that. Wonder where it went. Okay, so we start off with this. We start off with, again, it's the function minus the limit, so it's going to be x squared minus 1 minus 3. There's f of x. There's what we think is the limit. And that's got to be less than epsilon. You with me?
Is the limit supposed to be the absolute value? Or is it supposed to be absolute?
No, it's supposed to be in the absolute value. So we're giving ourselves, we can go up epsilon and we can go minus epsilon. And then what we're trying to do is we're trying to find out how big is delta on either side of the point of interest, which is 2. With me there? Okay. So this is x squared minus 4 less than epsilon. Which I'm going to do that little trick where we introduce a negative and make call it a 3-sided inequality.
Why do we do that? Just so it's easy to draw any two equations, right?
Yeah, so you don't need two equations, because again, you'd have to break it into this one. You'd have to break it into x squared minus 4 is less than epsilon. And the other one would be x squared minus 4 is greater than negative epsilon. And you'd have to solve each one of those separately and then put the answers together.
So straight in one
Yep.
equation.
Yep. Next step, add 4. So this is going to be 4 minus epsilon. And notice, this is one reason why I like doing it this way. You can see the uniformity, and you can see what we're talking about geometrically. So this is going to be up and down, okay? And then let's see, how do you get rid of the square? You have to take a square root, right? Okay, now, as long as we're dealing with really small epsilons, let's say epsilons that are smaller than at least 4, is that a positive number? And is that a positive number? Is it okay to just go through and take a square root of everything? Okay, so we're going to take the square root here, square root here, square root here. So that means we are at square root of 4 minus epsilon. This is x, and this is square root of 4 plus epsilon. Radical 4 minus epsilon is a little smaller than 2, right? It's a little bit smaller than 4, so take the square root of something a little smaller than 4, you're going to get something a little smaller than 2, right? Okay. Square root of this is a little bigger than 2, right? Okay, so let's take a look at this. What we're doing is we're saying follow this one over here. Whoops. And you're going to get something on this side. Follow this one over here, and you're going to get something on that side. So 2 is in the middle. Radical 4 plus epsilon is over here, and radical 4 minus epsilon is over here. And then again, just like normal, right there, we're going to figure out what delta 1 is, and right here, we're going to figure out what delta 2 is. Okay, everybody clear on the idea? Can somebody tell me without looking below, because hopefully you haven't had time to even look below, which one's going to be smaller? Delta 1 or delta 2? Okay, how many say delta 1?
They're equal?
How many say delta 2? How many say they're equal? Just to be argumentative?
Yeah.
Or you think, okay. Okay, it is delta 2. Delta 2 is going to be the smaller of the two. Can somebody tell me why? Just raise your hand if you can tell me why delta 2 is going to be smaller. Jen?
Because the slope is steeper.
Yeah, it's steeper on this side. It's going to cover that epsilon units quicker than it is over here because it's just slightly more shallow. So what is delta 2? Well, it's going to be square root of 4 plus epsilon minus 2. That's what delta 2 is. What is delta 1? It's going to be, careful here, you want to make sure delta is positive. It's going to be 2, because that's the bigger of these two numbers, 2 minus radical 4 minus epsilon. Okay? Now, I'm done. I mean, writing it up and showing how to do this would be fine. If you wanted to see if you understand this and actually buy that that is a proof that the delta that we choose would be this one right here, pick a small epsilon. Okay? Calculate what delta would be. Calculate what radical 4 plus a small number minus 2 would be. And then see if in fact it truly is within whatever epsilon, whether you go to the right or to the left of 2. So go up that much, go down that much, and see if you're still within whatever epsilon was of the limit 3. Okay? It's a fun little practice. Okay? You don't have anything more difficult on that on the assignment. There are lots of them that are pretty easy. You've got pictures for them. And I think on the homework, I think I said focus on the problems numbered 26 and before or 24 and before.
Just on the homework problems numbered up to and including.
Okay, they get a little